because there is no like algebra or anything like that. Like it's all going to be just like thinking through it and analyzing it and thinking in terms of infinity. So it is really going to be a different type of examples that we're looking at. To keep things consistent, I am going to kind of review back, and like some of the problems we do today will be intuitively. Some of them are going to be limits analytically or direct subs. I want to make sure that our brains can switch between the different type of limits that we do have. So to start off, I did want to review some prereq skills. And those prereq skills are basically the graphs of exponential functions and the log function. Because we see these a lot with limits, and I just know students have probably forgotten these, or especially have forgotten the natural log one. So I did just want to kind of review those with you, and then we'll move into like the calculus. So the first thing I wanted to review is the e to the x function. We know that is an exponential function. Some of the characteristics of it, it does have a y-intercept at 0, 1, and it has an asymptote, a horizontal one, at y is equal to 0. And then we also have the natural log graph. It's the inverse of e to the x. So it has a vertical asymptote. And for it, it's going to cross at not 0, 1, but at 1, 0. And that's because the natural log of 1 is 0. And instead of having a horizontal asymptote, it has the vertical one at x is equal to 0. So those are some prereq skills that you should have. Next to it, I just have some calculus questions just so we can connect the prerequisite skill of knowing the graphs to the calculus of limits. So like for this first one, I have h of x being e to the x. If I want to find the limit as x goes to 0 of e to the x, we can just do direct sub. So we know that whenever we try to find the limit first, we always want to do direct substitution. E to the 0th power is 1. Problems where we cannot do direct substitution is when we are approaching the infinity. So I have x is going to infinity and x is going to negative infinity. This technically I would consider something intuitive because you just have to think about what the graph looks like. Knowing what the graph looks like, if I say what's the limit as x goes to infinity, for e to the x, what is going to be the answer for the limit as x going to infinity? If anyone wants to take that answer.
Does not exist.
Does not exist. So the answer is, I'm going to put equal there, but it is d and e. Why is it d and e? Is because it's going towards positive infinity. What about the limit as x goes to negative infinity?
0.
0.
That's going to be 0. So we can look at the graph and we know that it is settling off at 0. And so I'm going to put HA there because our horizontal asymptote is where that information is coming from. So that's kind of us blending together some prereqs with the calculus. Then we also have the limit of this natural log function. So one thing I want to be clear, natural log is weird because it only exists when x is greater than 0. So if you notice, when I have the limit as x goes to 0, I put the limit as x goes to 0 from the right because technically you can't even consider the limit going towards 0. You can't come into it from both sides, which is also why this third question I'm going to cross off, because it just doesn't make sense in context. Like you can't go to negative infinity because x itself is not going to negative infinity. It's not within the domain of the function. So we're just not going to even consider that third part. The first part we can though. X is going to 0 from the right hand side. What will we say the limit as x goes to 0 from the right hand side is for this natural log function? Where is it headed?
Negative or does not
Negative
exist.
infinity. So yes, correct, does not exist. Why is it does not exist? Because it goes to negative infinity. I'm going to put a box around this because natural log shows up a lot. And I just want you to go ahead and commit to memory if you haven't already. And that is that the limit as x goes to 0 from the right of natural log of x does not exist because negative infinity. That negative infinity is important for some things we'll see later this period. And then the other one, the limit as x goes to infinity, this graph is always increasing, just like e to the x. Doesn't increase as quickly, but it is still going to infinity. So it also will be d and e, with the reason being infinity. So one thing that we're going to look at today is you're going to hear me use this phrase often, and that phrase is some infinities are bigger than other infinities. And what I mean by that, both of these graphs, as x goes to positive infinity, both of these graphs are approaching positive infinity. They're both increasing forever and ever. But I would argue that for one of these graphs, its infinity is larger than the other's infinity. Which one would you say has the larger infinity, the e to the x or the natural log of x?
E to the x.
E to the
E
x.
to the x. It's going so much faster, e to the x, that when you go towards infinity, if you were to compare the two, e to the x is always going to win out because it is increasing so much faster. Which brings us to kind of this first intuitive method we have. I'm not really going to call this like the formula or the steps, but it is a method. And so this was a flow chart we looked at last week. We saw that, if we get a real number, that's our answer. If we get a number over 0, limit is automatically d and e. If we get 0 or 0, which is one of our indeterminate cases, we have different types of algebra that we can try, factor and cancel, rationalizing, or maybe some other algebra. Infinity over infinity is another indeterminate case. And mainly what we need to do is to figure out which infinity is more important. And so one method I have, I call it FEPL, which is definitely an acronym, made up word, but it allows me to determine which infinities are more important. And it's mainly going to be used when x is going towards infinity. Actually, I typed this in, so I'm going to switch it over. Or maybe I didn't. So we're going to use FEPL, where x is going to go to infinity. And so you're like, well, what is FEPL? It's definitely not in your calculus textbook. It's something that's just made up, a useful thing to use. And what FEPL stands for is the types of functions we encounter in BC calculus. So again, it is going to be useful for when x is going towards positive infinity. It's not so useful when x is going towards negative infinity or things like that, or to a number. It's really only going to be useful when going towards positive infinity. And what FEPL stands for, the first part of FEPL is going to be the fastest growth, whereas the L is going to be the slowest growth. Or another way to say that, F is going to have the biggest infinity to L, which is going to have the smallest infinity. F is going to stand for factorial. E stands for exponential. P stands for polynomial or power function. And then L stands for logarithmic. I think most of us know what these look like. So factorial is that exclamation mark we know we have. Exponential is when the x is in the exponent. A polynomial, or power, is when x is the base and a number is the exponent. And then logarithmic could either be the natural log or a log of any other base. And that blue is a little hard to read. And so one use of FEPL, it's not something you will use every time, but in some ways, if you ever have a fraction and you're trying to compare numerators and denominators, it will help you figure out which side of that fraction is going to have the larger infinity. Any questions before we look at the example? All right, so here are the examples I've picked out. There are 6 of them. I will say some of these use FEPL, some of these do not use FEPL. But I did this to kind of make sure that we can compare and contrast the different types of problems. So these are all fractions. They all have like a similar look to them. But some of them are going to be easier to approach using FEPL than others. So I'll go ahead and give you some time to write those down. One thing about limits intuitively is we don't really have to show work. Like by calling them intuitively, it means we're just thinking through all of this in our head. Some students will write down like notes to themselves to help them figure it out, which is what I'll do while giving notes. But most of these can be done just kind of like completely in your head. And so I used just two functions. The first one in the red box was x squared over e to the x. Chose that one because I don't think most of us know what that graph looks like. Be surprised if you did. And then for the blue one, I chose x squared over the natural log of x. Looking at these, if we think about it in terms of row 1, row 2, or row 3, which one would you probably use the FEPL method for? And how would you know?
Row 1.
Row 1, and how do you know, Anna?
Because x is approaching in positive infinity.
X is approaching positive infinity. So we're not going to get used to using FEPL all the time. So let's talk about how FEPL works. So when you're looking at FEPL, we basically know some things are true in math. So let's review what we talked about last week, especially when we're dealing with infinities. I know if I have a number over infinity, what is that going to be equal to in terms of a limit when you have a number divided by infinity? Any suggestions?
0.
0. So when the denominator is really big, we know overall this is going to go towards 0. If you have infinity over a number, dividing infinity by a number is not going to do anything, like it's still going to be infinity. So the way that we can kind of approach this, so if I'm looking at this first one, you could technically plug in infinity, but if you plug in infinity, you just have infinity squared over e to the infinity. Well, infinity squared is still infinity. E to the infinity is still infinity, so we're not really getting anywhere. But we can use FEPL. X squared, the x is the base, so we know that is a polynomial. E to the x is an exponential. So we have a polynomial over an exponential. Which one is going to be the bigger infinity? The numerator or the denominator?
Denominator.
Denominator. So the way I think about it is I have like, okay, x squared, squaring infinity is a huge number, but e to the infinity is even bigger. So this one I have a bigger infinity on the bottom. So what do we think this limit is going to be overall?
0.
0, correct. So this limit is 0. Some information we also know. Going towards infinity, even though we don't know what this graph looks like, there is going to be a horizontal asymptote at 0, at least on the positive side of the graph. So that's how limits can kind of help us figure out what these graphs look like if we're not using a calculator. Let's try that same thing in the other first row. So I have the limit as x goes to infinity of x squared over the natural log of x. Well, if you plug in infinity, like it's going to be infinity over infinity. So we need to figure out which one's the bigger one. I have a polynomial over a log. Which one is going to be the larger infinity? Which one is growing fastest, the numerator or the denominator?
Numerator.
Numerator this time. So this time I have the big infinity at top, smaller one on the bottom. Well, if the bigger infinity is on top, what do you think that fraction is going to go to overall?
Infinity.
Infinity, and if a limit is going towards infinity, what do we say it is?
Does not exist.
Does not exist. So short way to think of this, big infinity on the bottom, limit is 0. Big infinity up top, the limit would be d and e. Now there's some other problems that look like we could use FEPL, but they're more just like, again, just like limits intuitively. Looking at this second row, not necessarily going to use FEPL because the x is going towards negative infinity. So what I'm going to write down is kind of what's happening in my head. So I know I'm squaring a really big number, and I'm dividing it by e to the negative of a really big number. Well, to help me think about what's happening in this one, in that numerator, I'm squaring a negative number. What happens when I square a negative number?
Positive.
It becomes positive, so that numerator is really just positive infinity. That denominator has a negative exponent. What can I do with that negative exponent to get rid of the negative part?
1 over the, or like, what is it called?
So we can put like 1 over, or the short way, if it's already in the denominator, we can just move it up into the numerator. So I can move it up into the numerator as e to the infinity. Well, infinity times e to the infinity is just going to go to infinity. So we know overall that this graph is just going to keep increasing forever. So what can we say about the limit for x goes to negative infinity of x squared over e to the x?
Does not exist.
It would be does not exist. If you ask for a reason, it's because it's going towards positive infinity. So moving on to this next one, this is going to be another one again where we just kind of think through it. So I have some number 0 coming in from the right, and it's being plugged into x squared over the natural log of 0. And we do need to kind of be careful here. So I know that the natural log of 0 is undefined. Like that is a math fact, that is true. But we want to be careful because we're not really plugging in 0 in this case. What number are we thinking of for this limit as x goes to 0 from the right?
Infinity? Or wait.
So like we're just thinking of a very, very
0.
small positive number. Like if we're coming into 0 from the right, like we're almost at 0, like we're infinitely close to 0, we just haven't hit 0 yet. So if I think about coming into 0 from the right-hand side,
Just 1.
so if I plug in a very small number and square it, what type of number is going to come out?
Something close to 0.
Something close to something even smaller. So when I'm thinking about this one again, this is all happening in my head. So this is where like the limits intuitive comes from. I basically have a very small number, teeny, teeny, tiny number, all over. I also want to think about what's happening to the natural log of x as I come into 0 from the right. So here's a review of what the natural log of x looks like. It had the asymptote. So what can we say the natural log of x is doing as you come close to 0 from the right-hand side? Where's it headed?
Negative.
Negative infinity.
Negative infinity. So in terms of the limit, if I have a very, very small number divided by a really, really huge number, even though it's negative, where would that limit be going overall?
0.
0. So that took a while for me to explain. As we do more and more of these, like you'll just be able to kind of look at it and be like, okay, small number over infinity, that's going to be 0. Infinity over a small number, that will be infinity. So that's where we were kind of get to. But that kind of shows you the thinking I have to go through to get to the answer. These last two I threw up on here because I realized in some years, like once I teach limits intuitively, students want to make like all of them intuitively, but we definitely don't want to forget that direct substitution is always the first thing you want to try. Like this first limit, you can clearly just plug in 1 squared, which is 1, e to the first power, which is e. So we do have a limit of 1 over e. Same thing with the second one. Plugging in e definitely works. Put this one on here to remind you that the natural log of e cancels out and just gives you 1. So the answer to that third one in the second column is just e squared. So again, don't get used to always doing these methods. We're going to have to use them together and pick the best method for each problem. Any questions on those 6? All right. So these were pretty easy to do FEPL, at least in that first row, because we only had 1 term in the numerator and 1 term in the denominator. So that does bring us like, what if we start having more complicated functions that just have more stuff going on. So to finish out the flowchart, and this will probably be the last thing we get to today after we do a few examples, underneath FEPL, another option you can do, I call it WMM. And WMM stands for what matters most. So that's where WWMM comes from. It's useful when you have x going towards plus or minus infinity, so it does work for both of them. It's also the one you want to use when you have more than one term. Because what matter most is going to allow you to do is it's going to allow you to kind of simplify the problem and only care about what matters most when you're at infinity. The way I kind of think about it, so Jeff Bezos, owner of Amazon, has billions and billions and billions of dollars. We'll just assume he has infinite, right? Billions of dollars. If he loses $10, he's not going to miss it. Like it's not going to go anywhere. He still has tons of money. Even if he loses $1,000, he still has so much money, it doesn't really matter. And that's what we're going to think about when it comes to these functions, is that when you're dealing with infinity, when you're dealing with very, very large numbers, sometimes like smaller numbers just don't matter anymore. So we're just going to kind of focus on what matters most in that particular function. Oftentimes we will also be using like what matters most and FEPL within the same problem. What matters most helps you like eliminate terms. FEPL can sometimes help you determine which terms matter the most. So some examples, I have these two to start off with. One to start off with kind of two simple rational expressions. That's going to be what we're most familiar with. I chose the same one. I have one, the limit as x goes to infinity. The other one, the limit as x goes to 2. First one or second one, which one is going to be more of a limit intuitively?
The first one.
The first one. So your big clue is if you're going to infinity, mathematically, you can't technically plug in infinity. You just have to kind of think through it. So that's going to be the intuitive one. And when I'm doing a limit intuitively, I want to think, hey, this is a rational function. In this rational function, what really matters? So when you're at infinity, looking in just the numerator right now, which one of those terms is going to matter most?
Probably x squared.
Probably x squared. And so if you think about it, squaring infinity, huge number. Multiplying infinity by 3, still a huge number, but not as big as squaring it. And then plus 2, who cares about adding 2 when you're already dealing with infinity? So what matters most in this one is x squared. If you have a polynomial, it's always going to be the highest degree or exponent. So in the numerator, only x squared matters. In the denominator, what looks like it's going to matter?
2x squared.
2x squared. So taking 8 away from infinity is not going to do anything. And so this answer I have in blue is sometimes called in calculus the end behavior model, because it represents what's happening at the extremes, what's happening at plus or minus infinity. Well, if we're looking at that end behavior model, if we try to simplify it, what's going to be left over? What happens to those x squareds?
They cancel.
They cancel. And what's left over is 1/2, and guess what? That is the limit to that problem. To connect this to some things you already know, 1/2 is also the horizontal asymptote. The horizontal asymptote would be at y is equal to 1/2 for this function. To connect this to some things you already know, you learned for a rational function, which is what this is, to find the horizontal asymptote, you had all these cases like when the degree of the numerator is less than the degree of the denominator, when the numerator degree was equal to the denominator, and when the numerator was bigger than the denominator. You have like all these different cases. This is the case where the numerator is equal to the denominator, and the rule you learned before calculus is just that the horizontal asymptote was the ratio of the coefficients. Now we know where that rule actually comes from. That rule comes from because at infinity, only the x squared and 2x squared terms matter, but that's going to simplify to give you 1/2. Looking at the second one, this is direct substitution. So one mistake I often see is people want to do what matters most all the time. So if on the second one, I'm about to do something wrong, don't always just pick what matters most. So like if you did this and then tried to plug in 2, that would be completely wrong. You can only simplify it like that by taking the highest terms when you're dealing in terms of infinity. This one, of course, is one that we would have done similar to last week analytically, where we can factor it pretty easily and then simplify and cancel. So don't always do what matters most unless you're going towards infinity. Any questions on that page? All right, I have one more kind of slide, and that's where I'm going to stop at today, and then we'll finish up tomorrow. What matters most can also help you decide some other types of problems, even ones where maybe you have like trig or a mixture of types of problems. So these are 3, they're all kind of related. The last 2 are the same function. The first one is a cosine of x over x. So when we think about in terms of infinity, we often want to think about like, 1, what matters most, but then also like what that function is doing at infinity. This first one, I had the limit as x goes to infinity of cosine of x over x. Now we can't decide what matters most because there's only one term in the numerator and one term in the denominator, but we still want to think kind of in our heads like what's happening at infinity. So as x goes to infinity, that denominator is always going to increase. That denominator is going to infinity. Someone remind us what's happening to cosine of x as you go to infinity.
It's oscillating.
It's oscillating. What's the highest and low value it's going to be?
1 and -1.
1 and -1. So we know the amplitude, it's basically always between -1 and 1. Sometimes it's 0, sometimes it's like √3/2, sometimes it's 1/2, but it's always between -1 and 1. So again, intuitively thinking about this one, if I have some number always between -1 and 1 divided by infinity, what is that limit going to be overall?
0.
0. So we have a number divided by infinity and we get 0. Where that changes, so if you look at the second one, I did x plus cosine of x in the numerator. We are going to infinity, so we would want to kind of think about what's mattering most in this problem. So if you think about, again, towards infinity, obviously in the denominator, we just have the x to deal with. In that numerator, which one is going to matter the most at infinity, the x or the cosine of x?
The x.
The x. So again, cosine stuck between -1 and 1. X, though, is always going to increase. So the end behavior model for this one is technically the limit as x goes to infinity of x over x. So the limit of the second one is going to be equal to what?
1.
1.
1. So they both cancel out and we are left with 1. This third one I put on here, just to begin, be careful. You can tell I'm emphasizing it because it does tend to be a common issue. Don't always use what matters most if you're not going towards infinity. It's like if you're going towards 0, go ahead and just plug it in and evaluate as normal. So I have the cosine, move my board, stressing out. We have 0 plus the cosine of 0 all over 0. Cosine of 0 is just 1. We know 1 over 0 is undefined, so the limit would be does not exist. Any questions on anything we've done so far? All right, so that's where I'm going to end class today. Tomorrow's notes won't be as long since I'm not going to teach you like another method. We're just going to be looking at more examples tomorrow. So your assignment, I am going to head and assign homework number 3. Homeworks 1 through 3 are due on Thursday. That's the day of your quiz. Make sure you read the instructions. I'm not assigning every problem. Do the number of problems that it tells you to do within each handout. If you finish it, you're more than welcome to go ahead and hit turn in. You'll still be able to access it in your OneNote, but I will go ahead and record the grades. If you're good to go, you can go ahead and log out. If you want to hang back and ask any questions these last 6 minutes or so of class, you can. But we will pick up with this tomorrow. Just looking at some examples, tomorrow's note should finish a little bit earlier. But if you're good to go, then goodbye, talk to you later. If you have any questions though, please hang out and get those answered before you leave.
Mr.
But
Brown.
that's it for me.
Mr. Brown.
What's up?